Hello, everyone. Welcome. Welcome to the second of our Commonwealth industry webinars, small-scale combined heat and power for universities, industrial, and commercial facility applications. We just have about 2 minutes until we get things kicked off. It's nice to see everyone filing in, so thank you for joining us today. We will be going over just a few quick items on participation and engagement in the presentation today, as well as follow-up stuff and of course the PDH aspect of the webinar. I know that a lot of good, valuable information. In just about a moment, we will be getting things kicked off. All right, folks are filing in. Hello, good morning. Maybe you're at a time zone where you are, it's not morning, so wherever you are, thanks for coming. Glad you're here. Okay, a few moments. All right, well, it is 11:45 Eastern Standard Time, so without further ado, let's get started. Again, thank you to everyone who is attending today, or in attendance this morning. Really appreciate it. Again, this is the industry webinar, Commonwealth Associates, our small-scale combined heat and power for university, industrial, and commercial facility applications webinar. This webinar will be available for on-demand streaming after the presentation. So if you find the information valuable and you'd like to share it, or you would like to get a rewatch, that will be available to you. We'll explain all that here in just a moment. So time has come. Let's get started. All right, if I could go to the next slide, please. A few housekeeping items first. I know a big question on people's minds is the PDH information. How do we acquire that? How does that count towards those professional development hours? So after the webinar ends, once the webinar ends, about an hour or so, is that later? After the webinar ends, you'll be getting an email from GoToWebinar and Commonwealth thanking you for being part of the presentation today. It will include a certificate saying that you attended this event today. It will also provide information. Basically, if you provide this email along with the certificate that says this is worth the PDH, certificate is proof that you completed it, that will count towards the PDH credit hour. Another item of housekeeping today, we really want to engage with you. We expect that there will be a lot of learning from our presenters, but we do want to answer your questions and handle any of your concerns or any thoughts that you have about the subject matter that we'll be talking about today. So if you have a question, or if a question comes up, there's a couple things you can do. One, if you look to the control panel section of your webinar interface, there is a place for questions. You can type your question there. There we have an asker. Sam Barnes is already in the questions, which is great. Hello, Sam. So you can ask your questions there, and then at question and answer time, I will be fielding those questions to our presenters. So make sure you know what that is. If something comes up, I want to know more about that. We'll definitely get your question at the end. If they're not able to answer your question for some reason, we'll make sure that we follow up afterwards. So really appreciate your participation. It does mean a lot. Another thing that we have on that sidebar is the chat. I mentioned the Q&A. We've got a chat. If you would like to communicate with myself or any of the folks presenting, or with each other throughout this presentation, you can use the chat function, and we will be right there, or at least I'll be there watching it throughout the presentation. We're going to be doing a couple user polls, so they will come up 2 different points throughout the presentation, the webinar. So make sure you just pay attention to the polls because we'd love to hear your feedback. I think participating in those polls will add a lot to how you, what you get out of this presentation. And then also there will be a post-webinar survey. These are very important to us as a company, and we really value thought leadership from other places as well. And to help us do better, we have a quick post-webinar survey that'll pop up. It's like 6 or 8 questions, something like that. Just a quick yeah, no. This kind of item might be interesting for next time. Just to see about your experience, what you liked, what you didn't like, and any feedback you may have. Again, the webinar is being recorded. You will be getting a link in that follow-up email with the PDH information with a link to the recording that you or anyone that you know will be able to watch later on. And just a quick promo for our upcoming webinar for the end of the summer, fall time is going to be on substation hardening. So make sure that you stay in touch with us across LinkedIn or through our monthly email newsletters, and we'll be getting more information about that as the day approaches. So with all that said, housekeeping is done. I'd like to introduce to you our illustrious presenters today. We have Michael Gibbs and Michael Hitchingham. I think first up we have Gibbs.
Yeah, Dale, thanks so much. Good morning, everyone. I'd like to echo Dale's sentiments. Appreciate you joining the webinar and allowing us to present this morning. My name is Mike Gibbs. I have about 17 years of engineering and project management experience in the power industry. I've worked for Commonwealth for the last 3 years, and I'm a mechanical engineer by degree. Michael Hitchingham.
Great, thank you very much. And Mike Hitchingham.
Yeah, good day. And this is the only time I'm going to make you look at my face, try to save some bandwidth. But good day, Mike Hitchingham. I am the Associate Director of Engineering for the Power Generation Department here at Commonwealth. My background is in mechanical engineering, but these days I do a lot of engineering and project management. I have approximately 25 years of experience in the power generation industry, including combined heat and power plants from about 0.5 megawatt up to city level generation and steam supply. So thank you everyone for joining us.
Thank you, Mike and Mike. Now, first up, Mike Gibbs. You're going to be kicking us off. Again, we'll have some polls coming up. We have a Q&A section later, so get in your questions. And thank you so much for being here today. Okay, Mike Gibbs, take it away.
Yeah, thanks again, Dale. Our agenda today, we'd like to start with defining what small combined heat power technology actually is. We'll discuss the different types of CHPs, and we'll then discuss the efficiency advantages for each CHP technology. After reviewing that, we will consider green initiatives and what green initiatives are out there and how clients can take advantage of the CHP technology. In parallel with that, we'd like to talk about the technical and economical considerations that clients can use to help determine if CHPs are right for their projects. And they'll use that to help evaluate each technology. At that point, I will throw it over to Michael Hitchingham, who will discuss a case study that deals with a CHP system tied to a university. I think, Dale, we have a poll question coming up, so I'll go to the next slide. And the poll question being, what is your experience with CHP?
Okay, the poll is launching right now. We'll have this open for just a few moments, usually 30 seconds or so. So what's your experience with CHP? Current owner operator, currently designing, constructing, evaluating as a future possibility, or no experience, here to learn. All right, we will, with about 54% of our, we're getting up there, 60. We'll wait a few more seconds before we close the poll and we can see our results. All right, close the poll now, and let's see what the results have to say for themselves. What is your current experience with CHP? With 82%, no experience, here to learn. Followed by 11% currently designing and constructing, and 7% evaluating as a future possibility. So thank you to those who participated. All right, Mike, back to you.
Yeah, perfect. Thank you, Dale. Thanks everybody for joining that poll. lucky enough, this presentation will be a very good intro to quite a few of you about CHPs. And as Dale mentioned, at the end, if we have any questions, we'll gladly try to answer those. And if we can't, we'll get back to you. So first part of our agenda is defining small-scale CHP. CHP, in essence, is a prime mover that is used to make electricity. The process that produces that electricity will also produce heat in the exhaust of the prime mover in the form of steam or hot water or hot air. Essentially, you want to use that hot air to use it elsewhere in the plant or use it elsewhere in the process of what you're looking to do. So some might ask, how small is small? I know the title of the presentation deals with universities, industrial, hospitals, medical. A lot of times we see CTGs, which I will explain more in a little bit. Those are from 1,200 kilowatts. Another technology is microturbines. You might see that 30 kilowatts to 330 kilowatts. And engines from 30 kilowatts to 18 megawatts. Obviously, you're looking at engines that are getting into a larger scale at 18 megawatts. And obviously, you can see too for the CTG, we didn't put an upper limit, as you know that can get into hundreds of megawatts if that's required for your use. Talk about types of CHPs. The first one is a CTG with a HRSG. What that means is that's a combustion turbine generator with a heat recovery steam generator. The next slide, I'm actually going to go through some flow diagrams and some pictures that might better explain the process here. But essentially what happens is the CTG is the combustion turbine generator will run, and the HRSG captures the CTG exhaust and uses the exhaust to heat water. The gas turbines, which is the CTG, are considered a strong market position, as shown by kind of the diagram on the right, because it's used in mass scale worldwide, and it generally has one of the lower capital costs per megawatt. So obviously, lowest cost per megawatt would be a big deal, and the maintenance costs are usually low for the prime mover for large CHP systems. Number two is the CTG HRSG combination, as I just explained, but then you're adding a steam turbine generator on the back end. Very similar. The steam turbine would actually extract energy from the pressurized steam from the HRSG to create more power. So you would have the CTG and the STG working to both produce power for your process. Number three is a boiler with a steam turbine generator. That is very similar to the CTG and the HRSG in option one, except that the boiler isn't a HRSG. The boiler gets its heat from some burning process of fuel, whether that's coal that you may have seen a decade or so ago, natural gas, or some sort of other fuel that we're seeing more recently. They'll burn that fuel, and then that burning will then proceed to provide what the steam turbine needs in the form of steam and energy to extract electricity. Number four is microturbine. I feel like a broken record, but they're all very similar in their initial design. You can imagine a microturbine being a smaller version or a smaller scale of a CTG. Microturbines can be described as a turbine engine with an added generator and electric power in a compact scaled down size. Microturbines are considered a secondary market position as they are much smaller in size compared to the CTG, and they typically cost more than the usage cost of reciprocating engines that you see in number six. Number five would be fuel cells. Fuel cells produce power electrochemically, similar to a battery. That process of reaction for the electrochemical will produce a heat, and then you can extract that heat and use it as you've done in the previous technologies mentioned. We do consider the fuel cells to be part of the emerging market position due to the high capital costs and lower exhaust temperatures, preventing it from a large, wide-scale use. And the last type of CHP would be the reciprocating engine with a HRSG. This is also known as a RICE engine, which is similar to a car engine. Much like the microturbine, this technology falls in the secondary market position. And if you don't mind, I would like to talk a little bit about the applications. The CTG and boiler options can be used for large-scale application, ranging from institutional power plants to large industrial facilities that maximize the power production and exhaust heat. Microturbines in the CHP application have been used a lot for building energy needs as well as industrial processes. Fuel cells are limited by their exhaust temperatures, as I mentioned previously, but they do have incredibly high environmental benefits. We are starting to see more fuel cells used in hospitals and data centers due to that emissions and environmental benefit. And then lastly, the RICE engines, those typical commercial applications could be a hospital, healthcare facility, food processing plants, institutional facilities, where the desired output may be less than what you might need from a typical CTG, but greater than the other CHP types. A benefit to the RICE engine CHP is the ability to use multiple smaller engines in series with each other to achieve the desired power output. And as I mentioned, I'm just going to quickly kind of show you the 6 process flows that you may see. Number 1 being the CTG with HRSG. You have the gas turbine, right? Its exhaust is going to heat up the HRSG water and you'll produce steam. Number 2 is the same system. This is the CTG with HRSG with the steam turbine generator. You're adding the second generator, so it'll take the hot water and the steam from the HRSG, and then that will also propel the turbine and produce more power. Number 3 would be the boiler with the STG, standard boiler, no different than what you might think about a tea kettle, right? You're going to boil up water, take the steam, turn the generator, produce electricity. Number 4 is the microturbine. So this one's kind of interesting. A lot of it is very, very internal. Up here and above, the CTG and the HRSG are not one piece of equipment. They're separated, connected by ducting. STG is connected by piping. Within this situation, a lot of this stuff is internal. You do have an exhaust, and it is much smaller than the CTG, as previously mentioned. Number 5, this is the fuel cell. You have the natural gas fuel processor, and then you have the power producing section with the fuel cells reacting electrochemically to each other, producing power and usable heat to use elsewhere in your process. And then last is number 6, which is the reciprocating engine. All of these flow paths are very similar, just the technology or the equipment is changing. You do have the engine, take the exhaust for a HRSG, you have your heating load and you have your power load. So at the end of the day, these CHP technologies, their 2 goals are to provide electricity, power and heat to be used elsewhere. So to talk about CHP efficiency, one driver for CHP is the efficiency gain compared to just the basic technology that can be used. I guess one question is that, did you know that over 60% of the energy used by the older electricity generating stations is lost in the form of heat exhausted to the atmosphere? Combine that with the loss of energy to the end user via distribution systems, the efficiency of older generator stations is below 40%. The idea to use the lost heat and to reduce the distribution losses has created a technology in the CHP that has drastically improved the efficiency in these processes. So if we look at the standalone here, RICE engine with reciprocating engine, around a 34% efficiency. CTG's around 30%. Now, boiler has a pretty high efficiency of 85% just by the technology itself of just boiling water and getting water out and heat out. Microturbines are low at 25%, and fuel cells are 50%. Depending on the prime mover, CHPs can reach 75% or higher efficiency. So compare that to the standalones. It's a really, really nice increase in efficiency. All in all, you look at this chart down here, I guess this graphic, right? Electric only average is 30%. Standard CHP is 58%, but when optimized multiple technologies, we're seeing as high as 90%. And I'll reemphasize that the main benefits to install a CHP for you or your clients are reduced energy costs, better efficiency, and increased energy reliability. To continue the efficiency discussion, I'd like to talk about heat rate for common generating stations. The heat rate is the amount of energy used by an electrical generator power plant to generate 1 kilowatt hour of electricity. The table here shows the heat rates for your common generation scenarios. A few are not applicable to the CH discussion, but it's good information regardless. As you can see from the table, the 3 best heat rates are the boiler with steam turbine, the CTG simple cycle, and the CTG with HRSG. All 3 of these have heat rates north of 10,000 BTU per kilowatts and around a thermal efficiency of 30 to 35%. From a client's perspective, if you're evaluating CHPs and if it's viable for you, I'd like to talk about a few technical considerations that you could research and take into account to evaluate if it's warranted for your situation. First technical consideration would be electrical load. Since different types of CHPs can efficiently provide different power outputs, understanding what the electrical load needed and what is required will help determine which CHP technology may be used. A second would be thermal load, which is similar to electrical load. As part of the CHP process, knowing what heating portion of the CHP required to do is vital. What is the goal of the CHP heating? Many of the universities, commercial sites, industrial sites, and hospitals that we've worked with use the heating portion to help heat common areas such as air heating, potentially water heating, even pools, laundry, kitchens. The exhaust heat can also be used to create low and high pressure steam to be used elsewhere on site, which you saw by the flow diagrams. A vital part of CHP is capturing that exhaust heat to use elsewhere in your process, which essentially is helping your process remain, or I guess increase in efficiency. Next would be how much energy is needed and for how long. Is this going to be a base load, or is it going to be a peaker that helps baseline existing energy sources? Typically, CHP systems are designed to meet the facility's year-round base load thermal demand. Knowing this will help determine which technology works the best for your application. After that, we'll talk about equipment redundancy. What are your requirements for equipment redundancy? That needs to be evaluated. Is a full-size backup required? Does the application require a total power output? That might make sense to have multiple pieces of CHP equipment. For instance, the RICE engines I mentioned before. In our experience, the importance of the process drives the equipment setup. For instance, if we're installing at a hospital, they may require backup generation, right? They may need full backup, where if we lose one, we got to go fully to another. That evaluation will help drive which technology you can use. Lastly, as mentioned before, the emissions control. What's required? Does it need to meet emission requirements? Does it need to be emissions free? Understanding what that emission requirement is will help determine the best CHP equipment to be used. A few considerations for economical evaluations, very similar to the technology or technological considerations. We have to look economically. A lot of times, the bottom dollar is a driver, whether we like it or not. So a few things we can look at are capital costs, O&M costs, potential savings, revenue, which might make the most money. And then also if we can avoid utility increases and outages, or be able to ride those waves, right, will help in evaluating your options. So to start off, on average, the gas turbine has the lowest average install cost in dollars per kilowatt. Following the gas turbine is the recip engine, then the micro turbine, and then fuel cell. For O&M costs, I mean, every technology is going to have maintenance and downtime, right, and outages. Understanding what that downtime and maintenance might look like and what needs to be serviced is vital. One example maybe for universities, when can the unit be shut down, right? Obviously with universities, they have summertime where the kids aren't in school, so the demands of the what I'll call power plant with a CHP would be lower, right? So maybe scheduling that outage during that time makes the most sense where you're not needing hot water as much, you're not needing as much power. So knowing that schedule, knowing that service schedule would be vital in helping determine which equipment makes sense. For savings and revenue, we look at energy bill, right? The higher the efficiency, maybe the lower the energy bill. If we can grab that excess heat, use it for HVAC heating, right? Now we don't have to power HVAC units for heat with electricity, right? We don't need to power or heat ancillary systems. So capturing that excess heat will allow us to reduce the need for maybe ancillary equipment in other processes. That's something to evaluate where you might be able to use that heat and save money elsewhere. Lastly, avoiding utility increases. That plays a huge role in the longevity of the system. With these systems, having a reliable energy supply means that the site has available electricity without interruption. Typically, most of these CHP systems are designed to operate without required tie to the electric grid, therefore allowing for a more reliable facility. And as I mentioned before, you might be able to ride the highs and lows prices. You know, we can avoid the high prices by providing our own electricity versus buying electricity from the grid. This is just a quick table that maps out kind of O&M costs for a site to help determine the economical feasibility of the project. Obviously, some things you might need to evaluate in parallel with the CHP. We already talked about the major maintenance, O&M costs, water consumption, right? Insurances, fees, taxes, leases, you know, everything that might go into having this process, this plant constructed and installed. You'll have a total operating cost. Then you got to look at fuel. You know, what's your fuel source? Natural gas, propane, whatever that might be. You'll have to look at consumption and how much that's going to cost to use it. And then obviously you're getting into more of a billing financial ledger here with the depreciation and total non-cash charges. And then you'll have your revenue and interest and taxes to look at as well. This chart is just simple. I won't dive into it too much. It's just a small example of the typical CTG degradation as it pertains to costs that you may see in projects. Part of the degradation of the equipment involves the wear and tear on the original components, the installation of spare parts. Also part of that degradation is how staff and operators will actually run the equipment. They'll need to be aware of how the equipment needs to be ran and the most efficient way to run it. The operating process and knowledge of the system will help ensure that the efficiency gains are kept at a high level and that the degradation of the system is slowed. As you can see here, you know, you have your peaks and valleys during outages. You obviously replace spare parts, clean things, make things more efficient so you can jump back up in your efficiency, and over time it's going to come back down and you just continue that process. Green incentives, green initiatives. There are quite a few green initiatives that are available. CHP systems offer savings compared to conventional separate heat and power systems. Unfortunately, due to initial capital costs and investment and regulations that limit the deployment of the CHP systems, the government, which is federal and local governments, have implemented policies and incentives that will help these processes overcome these regulations. A few of these policies will help lower initial costs and help the regulatory process become more efficient. Listed here are a few options that I'm going to just kind of briefly talk about at a high level. If this is something obviously you're interested in for yourself and for a client, definitely diving into these would make sense as part of the process of evaluating a CHP as an option. The first one is green bond. It's a fixed income debt instrument in which an issuer, which is typically the corporation or the government or a financial institution borrows a large sum of money from investors for use in a sustainability-focused project. The green bonds work similarly to a traditional bond issuance, except the funds are slated for use in energy efficiency, renewable energy, or other projects that meet certain sustainability requirements. That's often formalized in a green bond framework developed by the issuer. Green bonds do typically involve one or more third-party firms, to underwrite, certify, and monitor the bond issuance. Next would be the CPACE. It actually stands for Commercial Property Assessed Clean Energy. That's energy improvements, or the thought is that the energy improvements can reduce operating costs, increase asset value, and improve tenant comfort and satisfaction. But most projects are capital intensive and take many years to pay back. So the CPACE is designed to overcome these obstacles, providing low cost, long-term financing for your commercial, industrial, and nonprofit building. These terms for the CPACE tend to be long, 20 to 30 years, because repayment is secured by the tax assessment, and that would be transferred to the next property owner. Traditional commercial loans are usually 7 to 10 years. For anything we buy, car, house, whatever, interest rates do play a part. They are competitive since the tax assessment mechanism is considered secure and low risk. Third would be the feed-in tariff. The feed-in tariff is a policy tool designed to promote the investment in renewable energy sources. This usually means promising small-scale producers of the energy, such as solar and wind energy, an above market price for what they deliver to the grid. They do guarantee grid access, meaning energy producers will have access to the grid. They do offer long-term contracts, anywhere from 15 to 25 years. And they also guarantee cost-based purchase prices, meaning that energy producers are paid in the proportion to the resources and capital expended in order to produce the energy. And then the last two, I'll kind of lump together: grants, rebates, and tax incentives. They are typically government funded and can come from local, state, or federal levels. They are ever changing, so I didn't want to go into too much detail about it. So a project now may be not viable per, whatever incentives exist next year. So just being aware that there are grants and tax incentives that can be used, but are ever evolving. Research into that would be vital in starting a CHP project. And before we jump to the case study with My Kitchen Ham, I would like to discuss a very high level steps required to implement a CHP or a CHP project. The steps to consider include all of the previous slides that I've gone through, as well as the technical and economical considerations. First, obviously, a technical screening should be completed. This technical screening should also include environmental impacts and potential regulation requirements. Generally, like any project that would require the addition of a generating unit, a preliminary system sizing process should be completed based on the thermal electrical demands needed at the site. As we talked about before, the thermal loads from the CHP will help drive the type of CHP equipment that you might use in your process. For potential regulatory requirements, a review of the incentives and regulations will determine which equipment type makes the most sense. Obviously, we want to try to help offset the initial high capital costs that are required for a lot of this equipment. And we'd also like to review the emission requirements. As mentioned before, fuel cells have an excellent or non-existent emissions, I guess. So if that's a vital evaluation component, then you obviously want to look at fuel cells. Next would be the economical analysis. We should complete one of those after you've looked at technical. This really ties to the efficiencies, right, and the financial gains through the efficiency gains. Looking at the O&M costs, looking at the depreciation of the equipment, as well as tying that back to the regulatory and looking at the incentives. How much money can you save up front on that high capital cost? You can also look at the depreciation, like I said, and equipment degradation. What's your payback? What's your time to pay back that equipment? And then I guess there are only a few determining factors that would need to go into the economic analysis, like I mentioned before. But then looking at the contracting approaches, I'm going to approach these very, very high level traditional contracting approaches, which is owner would hire a consulting engineer to prepare specs and drawings, owner would purchase equipment, and then they hire a constructor. Next would be EPC or EPCM, which is engineering, procurement, and construction management. Owner would purchase a full service company to handle all aspects of the project. And then you have partial turnkey and full turnkey. Those can also be EPC type projects. Owner only has one contract, and they hire one firm to do it all. So that is the end of my presentation. Once again, thank you for letting me present to you this morning, and I will pass that over to Michael Hitchingham. We'll go over a case study performed by Commonwealth at a university. I apologize. There is a poll in between. So this poll, we're asking which CHP technology do you have the most familiarity with?
All right, thank you, Mike. I'll be launching that here right now. Which technology do you have most familiarity with? We'll have this open for about a minute. Please select one. CPG with HRFG, CPG with HRFG, SCG, boiler with SCG, microturbines or reciprocating engines, HRSG. We'd love to hear your perspective on what experience, what you've worked with, and to see what the makeup of the audience is. So we've got about 30 seconds in or so. We'll go for a few more. All right, as we get close to the end, there does seem to be some rising to the top of a few of our technologies here. Okay, let's close it up and see where we are. Which technologies have you the most familiarity with? Number one, with 48% of those polling, boiler with SCG. Tied for second is reciprocating engines with HRSG, CTG, and HRSG and SCG, and then the other two at 13 and 14%. So thank you all for participating. And now it's time for Mike Hitchingham with the case study.
Thank you, Del, and thank you, Mike. So now I'd like to go through a recent project Commonwealth supported from preliminary design through completion. As a history buff, I apologize, I'm going to give you more background than you need, but Eastern Michigan University, or Michigan State Normal School as it was known back then, was founded in 1849 as the first normal college in Michigan and the second public university. For the record, the first public university in Michigan was right next door at the University of Michigan. Go Blue. For those that do not know, Normal College was used to teach elementary and secondary teachers, and when Eastern was founded, the state of Michigan had only been admitted to the Union for 12 years, and it was the first educator training school west of the Allegheny Mountains. Eastern grew from a few hundred students in those early days to a few thousand by the 1950s, as you can see from this chart. It then saw significant gains in enrollment from 1960 to 1970 after adding graduate programs and officially becoming Eastern Michigan University. Major expansion occurred with 13 new resident halls and 5 new academic buildings in both a football and baseball stadium. And after a brief cooling off period, expansion resumed in 1980 with 10 new buildings by the year 2000. Eastern saw enrollment peak around 1990 at over 26,000 students, and all the new buildings and students put a strain on the utility systems at the campus, leading to plant expansion. In recent years, Eastern has struggled with student enrollment in line with most colleges in Michigan following the pandemic, and continues to look for ways to improve efficiencies and sustainability both at the heating plant as well as throughout the campus. The heating plant currently serves over 120 buildings, with approximately 99% of the campus buildings using the steam for heating, hot water, and cooking. The steam is distributed to the campus through tunnels, some of which date back to the early 1900s. So they're very good at using their steam throughout their campus. So next slide, Mike. The original physical plant, built in the 1900s, supplied steam to just a few nearby buildings, including the former Ford Hall through one of the tunnels that is still in use today. And as the campus grew, the heating load grew, and in 1951, the university built the current heating plant to provide steam to the expanding campus buildings for heating and hot water. In 1987, they installed a solar 60 CTG, and the heating plant began to generate electricity. Natural gas was burned in an industrial grade gas turbine coupled to a generator, producing roughly half the electricity consumed on campus. And as Mike said, it was only operating at an efficiency of about 30%. But with the addition of the exhaust heat from the CTG used to convert water to steam, it improved the efficiency and also provided for campus heating and cooling. When the system is not being used, campus steam needs were still supplied by the 3 conventional steam boilers that existed. By the 2010s, the existing CHP was still meeting close to 50% of the campus electrical needs, even with the expansions, due to more efficient equipment. But Eastern wanted to decrease their dependency on the local utility and eventually replace the solar Taurus 60 with a solar Taurus 70 and a new fired HRSG to increase electrical output by 75%. It also increased their steam capabilities and accounted for future continued expansion on campus. To get to that new configuration, a preliminary screening study was performed, and Eastern Michigan had multiple goals. First and foremost, they were seeking savings from additional generation to minimize electricity purchased from the grid. Second, it was critical to maintain operation during construction. They could purchase electricity from the grid to counter not having the existing CTG, but replacing the steam supply during construction would have been cost prohibitive, and it would have hurt the viability of the project payback period. Third, while they do typically import a portion of their electrical needs, they did want the ability to operate in island mode as a backup for resiliency to outside forces. They didn't want to be held to the local utility's ability to provide power when severe storms hit. And lastly, they were also looking to add black start capability to allow a restart if they were in island mode and no outside power was available. The 2003 blackout that I'm sure many of us remember, especially those that have been in the industry for a bit, impacted large portions of New York, Pennsylvania, Ohio, Michigan, and Canada, and brought about an understanding that the capability to start up without outside sources and then operate in island mode would improve their reliability for their customers, which are the students and the faculty. With the Taurus 60 nearing its 30-year planned life, Eastern began looking at options for its replacement. To support the RFP, Commonwealth investigated the campus's peak steam and electricity usage. Ideally, you pull the data from the past few years in hourly or daily increments to look for trends, because it isn't as simple as finding the maximum output and sizing everything to that. You need to keep down the need for potential turn down of equipment to ensure it meets your needs so that you can supply both the maximum and the lower levels. And if you're unable to do so, you may need to install multiple smaller units to increase the turn down range. Conversations were also had with university staff to determine how they wanted to operate the facility. And in this case, as mentioned before, they were looking for the capability to island from the power grid in case of an outage. When in the planning stages, Commonwealth also looked at the level of redundancy, just as Mike had mentioned, needed for all aspects of the project. Numerous configurations were possible, so they had to investigate if a single generator was sufficient or if 2 CTGs with matching HRSGs would be better to meet load variations and protect against downtime. But in the end, the campus has the ability to draw 100% of its power needs from the grid, so multiple generators were not required. If this CTG went down, then they would just pull from the grid. And it was known that steam could be provided from the existing boilers as a backup. With this understanding, they knew they could install a single CTG HRSG train and still have the needed redundancy. A similar evaluation, though, was performed for all the remaining equipment, right down to control valves and circuit breakers. So once we kind of knew what the configuration was, you took that information, put it into some thermal software, to model the plant with the various CTG makes and models, using the local ambient conditions to determine overall predicted performance, to also aid in determining the configuration and available redundancy. And then one final criteria for this situation was the university's contractual obligations with their local utility. In this case, they have LDs if they export power when not called for, and wanted to ensure a consistent indraw from the grid, which was taken into account throughout the project. So for Eastern, there really was no benefit to oversizing the generator capability. Next slide. So as I mentioned, you need to take a look at the historical data, and here we see a sample of the data used in the evaluation for one school year from September to August. The red line shows the electrical demand, which for this year ranged from approximately 4.3 megawatts up to 9.7 megawatts. But if you look closer, there's a definite normal band from about 4.7 to 7.5 megawatts. And then the CTG they ended up putting in is capable up to 7.8 megawatts. So in their normal band, they can cover their full load as needed. Not surprisingly, the heating load is more varied thanks to our wonderful Michigan winters, with a floor in the August timeframe with students off campus and only minimal hot water needs, but peaking in the January to February timeframe when the coldest temperatures occur during the second semester. All right, so during the preliminary engineering phase, multiple options were investigated, including upgrading the boilers to cover the new steam needs and maintaining the existing CTG for an additional period. They looked at a fuel cell system for generating electricity to try to improve their sustainability, but the technology just was not where it needed to be at the time for their needs. And in the end, they opted to upgrade the CTG and HRSG to provide more electricity and steam with larger and more efficient equipment. Also investigated at this time was the potential contracting methods, just like Mike had discussed. They looked at numerous contracting approaches, including a DBOOM, which I don't think Mike mentioned, which is a design, build, own, operate, and maintain contract that puts all aspects of the project on a single entity for an agreed price for a set period of supply. But you can also look at, as the owner, maybe you want to hire your own engineering firm, bid out the installation, and potentially bid out the equipment purchase to a contractor. To improve schedule, you may have to purchase the major equipment yourself ahead of bringing on a contractor and then turn over delivery and installation to them. So there are numerous types of contracts, and frankly, I'm a technical guy, so I'm not going to go into them all. But we definitely have people at Commonwealth that can support investigating the best contracting approach for you. So Eastern Michigan decided on a contracting approach of bringing on an EPC contractor, so engineer, procure, construct contractor, to build and test the facility before turning it over to Eastern Michigan to own and operate after successful performance testing. And for this project, ENGIE was selected as the EPC contractor and an energy performance contract, so another EPC. But an energy performance contract, ENGIE was not only responsible for building the new plant, but also provided guaranteed energy savings to Eastern. But at the end of the project, Eastern still owned all of the equipment. So as I've mentioned a few times already, the new equipment consisted of a new Solar Taurus 70. And the fired HRSG was manufactured by E-Tech. The picture on the left is inside the new Solar Taurus 70 enclosure. And then on the right, you see a site plan of its placement along with the HRSG just below it and the ductwork connecting them. The new HRSG was significantly larger and ended up replacing one of the old boilers while the other two boilers supplied steam during the summer. And then you can also see exhaust stack shown here, which is that bold square there on the left side of the right picture. Also has a bypass to allow operation of the CTG if steam production is not required or if it's being provided by the boilers. So whether you're upgrading like Eastern did, or you're building a new CHP, the selection of the ancillary equipment is just as important. So since in most places, natural gas supply to site is at a lower pressure than is needed for CTGs, 100% redundant fuel gas compressors were installed on site. Similarly, the existing air compressors were undersized for a larger CTG, so new redundant air compressors were installed within the existing building. At that time, they also did evaluations on performance to determine if a single set of compressors could supply the entire plant with the needed pressure, or if maybe they needed smaller compressors that would just handle the controls and the air tools and get larger compressors for the CTG air needs. In the end, it was determined single set of compressed air system was installed. So in the upper right, we also have just a picture of an inlet air filter. In new builds, it is often simple to implement the inlet air filter, as you can plan the building around the manufacturer's supplied scope. But at Eastern, the building was already in place, so the inlet air duct needed to be worked around the existing space limitations. As is the case with Eastern, if additional ductwork is needed on the inlet, the extra pressure drop must be taken into account for the CTG performance. All right, so since this project was a replacement of the existing CTG, demolition also had to be considered. As I mentioned, the existing CTG and HRSG were in line. You can see them in the light gray near the top of this picture. But due to the size of the new equipment, that configuration would no longer work with the existing building confines. You know, the HRSG would have ended up outside. In the end, boiler 3, north of the 2 other boilers, was demolished to make way for the new HRSG, and the new CTG was placed in the old combined location. This configuration required additional ductwork and also a modification to the exhaust stack. Again, 2 remaining boilers were able to provide steam throughout the project to the campus while they did this work. So here on the left, you can see the plant before construction, and on the right, you can see the upgraded plant. You see there was little changed with the building itself. If you drove by 1 year and came back 5 years later, odds are you wouldn't even notice. But boiler 3 stack was demolished and the roof was repaired in that location. And the existing CTG exhaust was also relocated, with that roof location also being repaired. Interesting point here is the modifications to the roof actually voided the 30-year warranty on the roof, which had only been completed a few years earlier. So while the roof penetrations may seem minor, the modifications released the previous roofer from their obligations and forced Eastern to take on a little risk if issues arise in the future. In the picture on the right, you can also see the new fuel gas compressors to the north of the building. There's 2 of them. And to the right of the building is the new reciprocal engine they used for black start capability. All right, just the thing all engineers love is aesthetics, but the heating plant is located along Oakwood Boulevard in Ypsilanti, Michigan. It leads to numerous student residences and is also in front of the main campus library. So there's plenty of both vehicle and foot traffic in the area. So not surprisingly, visual aesthetics played a role in the modifications. In addition, the plant is across the road from a residential neighborhood, so noise was not only a campus issue, but also would have raised neighborly concerns if it got to be too loud. The goal of the project was to maintain or improve the exterior look of the building and any equipment placed outdoors. So they did investigate placing equipment on the roof to try to hide it, but as you saw, the equipment either ended up within the building or outdoors at grade for structural reasons. The outdoor equipment was then concealed using fencing, berms, and trees, with the added benefit of the berms and trees mitigating some of the noise from the reciprocal engine and the compressors. And while the reciprocal engines can be loud, the placement was such that when it's needed, the noise would be directed towards campus and not the neighborhood, which is shielded by the building. The engine is typically only started periodically for testing, and those tests can be scheduled to minimize impact to campus activities. Okay, so we've had some big pieces of equipment. So in order to remove the existing CTG, HRSG, and boiler, as well as install the new equipment, the end of the building was opened with the siding and louvers saved to be reinstalled at the end of the project. Saving those allowed the finished product to look the same, since the new siding would have most likely been a different shade due to weathering. So the contractor took great care in removing those items. So as you saw earlier on the overhead view, the new HRSG and CTG were both tighter fits than the existing equipment, but by sliding the HRSG in diagonally and then turning it into place first, then sliding the CTG in, and finally installing the ductwork connecting them, the equipment was installed in a relatively short period of time. Process was aided by the contractor's use of 3D modeling software, and you can see from that picture, it was quite an effort to get things in there. All right, so now I'd like to go through some of the different disciplines just to discuss some of the upgrades that may or may not be on the forefront of your mind as you begin a project. First off, I'm going to start with the controls, partially to get it out of the way since it's not my expertise, but also because it is probably the most important aspect of these projects, particularly when connecting to the grid. Please note, this is a stock photo. This is not Eastern Michigan's control room. Theirs is much smaller, but we have performed upgrades at plants with similar equipment, and with the original CHP built in the 1980s, there were still some of these items that you see here in their control room. The new equipment controls were needed to be integrated into the existing control room to allow for seamless operation of the plant. Controls looked at how to operate the plant to handle the fluctuating electric loads, the fluctuating heating loads, and to do so as automated as the owner desires. You have owners that may desire the plant to go into island mode automatically, or you may have owners that want their staff to have control over that. So they may want to have more control over how that switch is made. Same for starting up boilers or CTGs if you have multiple, down to air compressors. How many hours do you want on each of your air compressors, and are you switching that automatically, or do you have someone pushing the buttons on the screen to get that done? These control upgrades and modifications also need to be done to support the plant's goal of operating throughout the construction. Wholesale changes should not be done all at once, or you run the risk of changes failing and your plant being crippled. There's nothing worse than having all the equipment there that you can't run because the ones and zeros aren't lined up correctly. Incremental changes to the existing or a transfer from an old system to a new one after sufficient testing is always prudent. So this goes back to the understanding that campuses cannot be shut down. Factories do not have long outages. The more pre-planning and engineering that can be done with flexibility during construction will lead to a successful project. So as we've talked about, the new CHP nearly doubled the electrical generation output from 4.5 to 7.8 megawatts. And this resulted in the need for electrical upgrades, both internally and also with the distribution from the heating plant to the campus. New equipment within the plant meant new MCCs. They had to upgrade other MCCs to accommodate the larger generator and other equipment. Additionally, cabling was added to handle the increased output, along with new controls in place to handle operation in island mode, along with potential black start scenario. Again, to the extent possible, new equipment was added prior to demoing the existing CTG and HRSG to minimize downtime with the final interconnects. So bottom right is the pad for the generator, and you can see all the electrical feeds are poking up there from the bottom to keep them away from public hands. In many campuses and industrial applications, you don't always know who will be around outdoor equipment, so you should always plan for the worst case scenario of a inquisitive passerby or someone who unfortunately may be a little more nefarious and want to intentionally damage something. So below grade aspects and locked cabinets can keep people out. But fences and cameras are also recommended in many locations. And if we went back to the overhead, you would see that the gas compressors were in fact enclosed in fencing. Okay, next slide. The mechanical installation was fairly straightforward. So just some final pictures from the facility during construction. In the upper left are the underground tie-ins for the fuel gas compressors. Collaboration between engineer, constructor, and owner during project development can aid in making installation as smooth as possible. But even then, especially with buried systems in existing areas, it is important that all stakeholders have flexibility during construction to make quick decisions and changes when unforeseen circumstances arise. To the right of that is the fuel gas supply train to the HRSG burner. Accessibility of valve trains is also an important aspect to keep in mind when laying out a plant. In this case, the valve train is along one of the main walkways in the plant, so maintenance staff walk by there frequently and they can just glance over and verify operation as they walk past. And then along the bottom row are just some, frankly, filler pictures of the steam drum, beautiful pipe support. Those that know me know I started in pipe stress, so I love my pipe supports. And the top of the HRSG with the safety relief valve. For CHP plants supplying steam, protecting the piping and in conjunction the people around the equipment from the pressure and temperature of steam can be a life or death situation. Proper sizing and installation of relief valves to protect from overpressurization often falls to the HRSG or boiler supplier, but every engineer should do their due diligence when reviewing to ensure proper sizing. In addition, steam piping will grow approximately 1 inch for every 100 degrees of temperature rise per every 100 feet. So thermal growth is, if it's not controlled properly, it can result in overstressed pipe and connections that could lead to catastrophic failures. And I think if we all go on YouTube, there's a fair number of these that you've seen at plants over the years. Steam piping should always be evaluated for stresses by a qualified engineer, as should any other high temperature or high pressure piping system. All right, so to wrap things up, I'm bringing it back to this slide that Mike already showed. You know, for the overall process of implementing a CHP or frankly any project, and Eastern Michigan followed each step with support from their owner's engineer and EPC partner. You know, Eastern had previous positive experience with their existing solar turbine, but they still evaluated other manufacturers on the market to verify purchasing another one of those was still the best option. Commonwealth supported them in then determining the right plant configuration and provided an economic analysis to help justify the upgrades based upon the additional electrical generation and ability to meet the growing steam demand. Decisions couldn't be made in a vacuum though. Like most places, the final decision had to come from higher up the chain, and presenting all this very technical information in a clear and concise format helps the non-technical decision makers in their evaluation. So from a contracting approach, multiple were looked at and based upon the evaluation of not just financial considerations, but also from a risk and stakeholder perspective, including stakeholders like the university's board, staff, students, or taxpayers. Their final contracting approach is what they felt best served them. From all that, an RFP was then developed, issued, and bids were evaluated with the selected contractor being negotiated with, leading to an award with ENGIE. ENGIE then took over on the design and construction side, so those two little plateaus, but they had oversight from Eastern Michigan staff and Commonwealth staff throughout the process. And this finally leads to everyone's favorite time of the project, closeout. So admittedly, by the end of the project, there have typically been a few bumps in the road and most people are just ready for the project to be done. But it is a critical final step in the process to ensure that the plan is operating as designed and the contractor has met all contractual obligations. And while communication is key throughout a project life cycle, It is especially important and often hard at the end to make sure there are no hard feelings and the final payments can be made. You know, the last thing you want to do is leave a bad taste in everyone's mouth after months of construction, when a very minor issue that likely has an easy solution, you end up fighting over it. If everyone just took a step back and looked at it with a clear mind, it likely would be easier to resolve. So with that, I would like to thank you for your time. I'm going to pass it back over to Del, see if there were any questions, and for his final closeout of this presentation. Thank you.
Thank you so much, Mike, and thank you everyone for joining us for that presentation. We have a few moments to do some Q&A time. I have the Q&A section open up, and we'll be going through these questions here in just a moment. So if you have a question, please bring them to the table through the questions widget in your control panel. We have a few to start. Yes, we do. Just a quick reminder that we will be sending out the webinar through a link in an email, a follow-up email from the presentation. So we look forward to hearing your feedback. That really goes a long way in helping us make the enjoyable and fun educational experiences for everyone. All right, let's get to some of our questions here. One moment, please. Okay, so our first one here is there a particular, and this could be for either of you to answer, is there a particular CHP technology that is more applicable for universities, hospitals, the campus application?
Get that one, Dale. Thanks. This is Mike Gibbs. I don't think so. I mean, I think there are multiple technologies that can be applied to probably most situations. I think going through that evaluation economically and technologically, technical considerations, that will help drive exactly what type of technology you're looking for. As Mike Hitchingham was showing the university, and that was a pretty large power plant, right? But you could also have a really small community hospital that doesn't need that big of a power plant. So you may be looking at a reciprocating engine, or you may be looking at some other smaller technology that will be applicable. So I think depending on your situation, there's probably quite a few technologies that can apply.
Yeah, and if you don't mind, I'm going to piggyback that just a little bit. It also comes down to market factors, to be honest. Especially we've all seen shortages of everything these days, but you may be able to get a savings on a reciprocal engine, potentially because someone bought it and then didn't buy, so you can get a savings on that. So really, it's ever changing as far as what may be the best option.
Mm-hmm. It's less of a one-size-fits type of test, and more of a lot more factors are taking part of that. Great, thank you for those answers. We have another one in today. It's, do you have any experience integrating solar arrays with CHP?
I guess I can jump into that, or Hitch, were you going to say something?
No, I was going to let you. You're our renewable guy. Come on.
So, I mean, yes. So we talked about kind of with the green initiatives and incentives that there are upfront incentives that will help drive tying renewables to this type of generation, right? There obviously is some interconnection that would need to be determined and studied. There are interconnection studies and other electrical studies that would need to be completed to ensure that that is capable to be completed or makes sense to be completed. But sure, yeah, tying renewable energy to any type of power generation is definitely an option.
Great, thank you, Mike. Mike Gibbs, that is. Question box is still open. We've got until about 1 o'clock, so feel free to put in your questions. And again, if it's something that we need to take offline, we definitely can. So we look forward to answering your questions. The next question we have is, I noticed on the overhead that while the gas compressors had a vents, the engine did not. What was the reasoning for that?
Okay, someone has a good eye. That is correct. The gas compressors were fenced in and the engine was not. As I mentioned, so all the electrical on the engine came up from the bottom. I did not mention that the natural gas supply also did come in from below inside the enclosure. So for the engine, it can be completely closed and the access ports can be locked so people can't get into it and do anything to that. Now with the gas compressors, the piping was exposed. There were valves that, they'd lock the valves, but if someone came up and cut the lock and potentially opened or closed a valve that shouldn't have been, as we all know, compressed gas can do some bad things. So that was the reasoning behind putting the fence in as an extra line of defense there.
Thank you. Thank you, Mike. Yeah. All right, that seems to wrap it up on the questions side of things. So thank you all for your questions and for participating in that. Again, if you have any other questions, feel free. You can respond to the emails that you're getting from us about the webinar, and we will make sure that those questions get to our guys over here. If you can go to the next slide. Just before we wrap some things up, I wanted to again thank everyone for coming. Again, my name is Del Belcher, Marketing Manager here at Commonwealth Associates. The PDH, it's coming when you, after the webinar ends, about an hour or so, you'll be getting that email with a thank you from us, as well as a certificate from the webinar about this session, with some information in the email saying that this email, along with the certificate, is enough to prove your PDH credit. You can turn that into wherever you need. That should be appropriate. And if not, please let me know and we'll work that out for you. Again, there's a post-webinar survey. So once I end this, or once you jump out, you'll have a survey that gives you a few questions about how we did. That feedback is very important. We try to use that to make each of these webinar experiences better for everyone. The webinar is recorded. In that follow-up email, you will be getting a link to stream it at a future date. If you'd like to share this webinar with someone else, revisit the information yourself. Our next webinar coming up in a few months, end of summer and beginning of fall, on substation hardening. That'll be a really great opportunity to learn some very interesting things that are emerging, and great way to start protecting those valuable resources. And lastly, our website, cai-engr.com, is our Commonwealth Associates website. Feel free to visit there, and we would love to hear what you have to say and check into our resources and other things that we have available to help get you set up with this small-scale combined heat and power. Again, on behalf of the team, I'm Del Belcher. Thank you for joining us for this webinar, and I hope to see you again soon. All right, have a great day, everyone.